they used South Mountain and the Blue Ridge as a screen, essentially, to move without the eyes of the Union on them. Then they had to get over the mountain. And so South Mountain became important.
Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Chris, continuing on in our Gettysburg Geology series, and this is part 6. Part 6 already. South Mountain is for me, I don't know. How does it influence the battle? How did it influence the battle?
Okay. So South Mountain is a significant mountain. You know, it's 2,100 feet plus elevation, whereas the Gettysburg Basin is closer to 600 feet above sea level. So you're talking about a difference of, on the order of 1,500 feet-ish. And so, the Confederates, they used South Mountain and the Blue Ridge south of it as a screen, essentially, to move and without the eyes of the Union on them. Then they had to get over the mountain. And so South Mountain became important because there is a fault that cuts right through South Mountain, and it makes for this really lower relief. It creates a pass, a gap, and it's wide. And the rock was good for moving heavy artillery and just lots of people and lots of equipment over the mountain kind of rapidly. So they didn't have to get very high. They were able to move pretty fast. So it was significant for that. And then it was also really significant in the retreat. They used it to come in. They used it to get out after the battle. And so it's geologically super important in the Battle of Gettysburg.
And it's a beautiful area. I mean, it's a stunning.
It's absolutely beautiful.
Stunning scenery. When we're up there and you can see out on clear days, you can almost kind of see out to the Atlantic, or you feel like you can, right? You look out to the east and you really see this Piedmont that's sloping away from you. That it's just a stunning viewpoint that you get. It's hard to capture the scale of it when you're on the battlefield looking to the west, like when we're standing on Seminary Ridge, looking to the west, or during our field trip episode. Go back to the first episode in this series if you want to see that. But you're looking back to the west and you can kind of make it out. You can see that there's hills there and there's ridges, and they're kind of stacked hills in the classic Blue Ridge idea that there's big ridges and there's ridges behind them, and you can see this sort of blue color to them. But really, when you're in South Mountain looking back the other way, it's more spectacular, and you kind of get a sense for the relief. This is a major barrier, especially back in the day.
To me, when you're in Gettysburg or around Gettysburg, let's say you said Seminary Ridge, if you're standing on that and you look west, you're looking at a wall. And this is the western wall to the Gettysburg half-graben that we talked about before in prior episodes.
Hey, Segway Award, Mr. Chris Bullhead here, half-graben. Let's talk about that transition a minute, because it's a sharp transition. It's a pretty sharp boundary when you go from Gettysburg, where you're sitting in this Triassic rift basin, like we talked before. Everything, including the York Haven sill, is dipping down into the west by about 15 to 20 degrees. All the sediments are kind of dipping down into the west. If you kind of follow that dip, you go to the west, you hit South Mountain. It's a pretty sharp boundary. There's not little foothills that you get rolling into the big hills. You kind of hit them right away. And the reason is because there's a big fault. It's abrupt. And usually abrupt means a fault in geology. And there's a big normal fault. It's called the border fault along these basins. On the west side, there's the border fault. It's normal fault. Here, image number 1, we just have from our introductory CampGeo content a normal fault, a schematic of a normal fault. It's just showing how this happens. You have to have extension. Pulling apart, there's a fault that happens, stuff drops down.
Yeah,
and
the only thing that this doesn't show is the listric nature to this half-graben. It doesn't show that kind of curved fault surface. That's the only thing, but everything else is the same. This is normal faulting, is when the hanging wall drops. That's the Gettysburg Basin. And the footwall goes up. So you're bringing, when that happens, when you thrust up the footwall like that, then you're bringing older rocks to the surface.
Yes.
And that's
good point. That's the story
crucial.
we're talking about.
That is the story. Absolutely.
When we were talking about doing this episode or this series, we didn't know how to do it. We were kind of thinking, well, should we structure it in geological time, start with the oldest first? And if we did that, we would have started with South Mountain and the Blue Ridge pretty early on in this process, but we decided to kind of do it in a more topographic sense. And so we're getting to this later because these are older rocks. We're going to be talking about much older rocks now. We're going to be going back into the 500 million years, sort of pre-Cambrian, Cambrian boundary here in this episode.
That's right. So let's back off a little bit here. This episode is all about the geology of South Mountain, and it played big into the Battle of Gettysburg, the battle and the retreat itself. But I just want to acknowledge something, because to me, it's like the elephant sitting behind me in the corner, is that this was really difficult. This was
this episode.
This episode, the geology of South Mountain is far from straightforward.
Oh my God! And understatement of the year award.
It was really
straightforward.
Yeah, it was really frustrating. Couple things, right? One is the geology is complicated because we have so much happening through pretty big amounts of time, and there's also not a ton of research to dive into on the geology of South Mountain itself. And then what you are able to find is complicated, It's so.
My God.
Yeah.
It's insanely complicated, right? I mean, this is a classic example, I think, of eastern and northeastern United States geology, that there was a bunch of work done on these areas a long time ago, 50s, 60s, 70s, right? A lot of that fundamental base level, what is this rock? What's the general age of it? A lot of that work's been done a long time ago. And there has not been a lot of work done revisiting it. There's certainly some. We found a couple papers that, looked at the geochemistry of South Mountain rhyolites, for instance. But this is a very classic, like, East Coast United States thing that people haven't revisited it in a while. And it's actually, I was really excited by this, Chris, because I read it and we were getting into this. It's like, there's so many cool things to do in South Mountain and in this area. Like, there's some cool tests to do that I think we're going to do in our lab. I'm going to get some undergrads. We're going to do some simple tests that kind of look to see if there's more meat on the bone in the science here. Because there's like this general story's been worked out, but the details are still pretty mushy.
Yeah,
and it's
so we're
really
going to stick to the general details then.
That's exactly right.
Like, I think there's something that's important here. This border fault that you've referred to and this tensional forces, this was the breakup of Pangaea. Part of the complexity comes from the rocks that are actually exposed in South Mountain have really nothing to do with that itself. These are older rocks that may represent actually the formation of a supercontinent that preceded Pangaea, Rodinia. And so really, you're talking about when you're in Gettysburg and you look at South Mountain, you look at this massive wall, you're looking at the formation of a supercontinent, then the breakup of that supercontinent, and then the formation of Pangaea and the breakup of Pangaea. All of that is recorded.
It's
within line
amazing.
Of sight. Yeah, it is.
You look at, that's an amazing thing to do. Go to Gettysburg, stand there, go to one of the towers, go to one of the lookouts and look to South Mountain and think about that. You're witnessing the creation, and destruction. You're standing on the last destruction of a supercontinent, but you can see that whole history. Now, I think also, Chris, that explains why it's so complicated, because you have two supercontinent forming and destroying events recorded in this area. Of course it's complicated. Of course the faults running through South Mountain are incredibly complicated. We're right next to the Ridge and Valley province. South Mountain and the Blue Ridge is kind of the first mountain range when you get into the Ridge and Valley province. And you just look at a satellite image, these are tortured, twisted, folded rocks. Like, this is complicated stuff. There's thrust sheets stacked on top of thrust sheets there. It's complicated, of course. And then we're here because of this normal fault. We have brought up older basement rocks that have witnessed a longer history. And so therefore it's quite complicated. So I think you're right. We need to kind of, go ahead.
Jesse, let's transition then into, if we're going to stay high level, which we need to,
for sanity's sake, if nothing else.
What's the overall structure of South Mountain? And we get into this thing that's called an anticlinorium. And I think a lot of beginning students are not familiar with that.
The term anticlinorium?
Yeah.
Or this
the term
region, you mean?
Itself. No, the term. Yep.
So let me turn to image number 2 here real quick, which is just showing we've kind of zoomed out. We're looking at, again, a LiDAR map topography of the region. Gettysburg is kind of in the north center. Down to the southwest of this, we have Gettysburg Basin and the Piedmont, which are kind of these flatter, low-lying things. We could kind of start to see the arms of the Chesapeake Bay just off the bottom of this image, the bottom right of this image. Then just to the west and the northwest of Gettysburg, we have the South Mountain, and then we have the Catoctin Mountains, which form part of the Blue Ridge mountain chain. Then as you move northwest of that, you have what's called the Great Valley. And the important thing here is that the Great Valley here kind of takes a bend up and to the right at the top of this image. It's kind of running, I don't know, northeast to southwest, and then it bends and curves over up near kind of Harrisburg. And that was really important, Chris. So we kind of see this barrier. That South Mountain is this great barrier that kind of wraps around Gettysburg. We have the Catoctin Mountains and the Blue Ridge down south. And that's the kind of setting for the topography, which we've talked about before. Why Gettysburg battle kind of happened in Gettysburg is because all roads lead to Gettysburg in this region because of South Mountain in part. Okay, what's an anticlinorium? Anticlinorium is a deviation from anticline, which anticline is just, it's the A shape. It's if you take a rock and fold it, squish it, fold it, the up A shapes, the ones where it folds up and then back down, that's an anticline.
Yeah. If you think about like wrinkling rock, it's the up wrinkle of a rock. That's an anticline.
Up wrinkle, yes. As opposed to the down wrinkle, which would be a syncline. An anticlinorium is just an anticline that has a bunch of little anticlines on it. And we usually use these terms to mean regional scale, like bigger
folds
scale
within a fold. Yep.
The master fold is the anticlinorium. The little folds would be anticlines on top of like folded. And yet that makes sense. It doesn't happen as much when you wrinkle a piece of paper that you get these multiple folds on little folds. But when you fold rocks, you get little folds, like parasitic folds. We call them little folds on top of bigger folds. This anticlinorium, the Blue Ridge anticlinorium, is defined or is really easy to see when you map the basalts of the Catoctin Formation. You can see that you've folded this. You've made a really tight fold. So you take a piece of paper, fold it, and you get an anticline, a really steep one, where the sides are almost parallel. It goes straight up, folds over, comes straight back down.
Yeah,
so that's
like an isocline.
anticline.
Yeah, yep.
This one, however, we have take that folded paper in your hands, and you tilt it away from you. So you tilt it down, and then you cut it in half. So you've turned the paper kind of 80 degrees, so it's pointing mostly down. You cut the paper in half, and now you see, if you look down on top of that, you see this kind of A shape where the top of the A is pointing to the north. That's kind of what we've got in the Blue Ridge anticlinorium, and South Mountain resides in the A part. The limbs of this thing run down to the south and kind of go out into and form the Catoctin Mountains down in Maryland and Northern Virginia. The Potomac kind of crosses down there. We've got series of ridges that are the arms of this A shape. So that's generally what the anticlinorium is. The South Mountain area is near the hinge point, the top, the bend in the anticlinorium here. How'd I do, Chris?
I don't know. Kind of confusing, to be honest.
Okay.
So I don't know. If you, like you said, you take that piece of paper and you fold it into that upfold, that's an anticline. But then you have several anticlines within it, right? That's your anticlinorium system. It's like if you take in a carpeted room and you have a file cabinet, a heavy file cabinet, and you need to move the file cabinet, but you can't pick it up. So instead, what you do is you just kind of shove the file cabinet over the carpeting. That's going to cause the carpet to rumple. So you're going to get multiple ridges and multiple dips and so on with this shoving of the file cabinet. That's your anticlinorian system that you're talking about. And then it's way more complex because then you have to fold it and you have to tilt it, or you have to bend it on its side basically, and then also tilt it from beneath. And so the geometry of this is quite complicated. I think we can just leave it at that. Does that
Okay.
that sound good? I don't know.
I'm confused by your analogy now too. So we've
Now, what are we talking about?
sufficiently just confused each other.
All right. I like my analogy better, but
Well, to each their own.
Yes.
Our analogies are okay. This is complicated, right? This is a complicated place. It's one big fold with a lot of little folds on top of it. One big regional fold, and if you zoom in, there's a bunch of little folds on top of this thing. That's what we're talking about. And we're up near the hinge of the fold. In South Mountain, it's near the hinge of the fold. Hinge of the monster big fold, the larger regional scale.
So let's get into the rocks themselves, Jesse. What's the geology of the rocks of South Mountain then? And these are awesome rocks. Yeah.
They're beautiful rocks, and they're a little counterintuitive when it comes to the topography, I guess, a little bit. First of all, they're old. They're not as old as, you and I like to think about rocks that are old, but they're pretty old. There's a lot of volcanic rocks. There are a lot of sediments, clastic sediments, conglomerates, and quartzites. Those are the kind of the two main types. And the breakup, we referred to the breakup of a supercontinent Rodinia here. Those rocks are represented in the Catoctin Formation, which is a bunch of basalt that is erupted. Chris, our last stop, we didn't record anything on it because we just did a real quick stop, but we stopped our last stop when we were together was on Catoctin Formation basalts that were metamorphosed into kind of had epidote all over them. Really, really pretty rocks.
It is a beautiful rock.
These things, there's a couple different generations of them. Some are older, 760 million years. Some are younger, 560 million years old. Most of them are the younger variety, 560 million years old. And they kind of go all up and down the Northeast from this part of the world, South Mountain, all the way down south into North Carolina, really. And so you can find little hints of these things all over the place. And this represented the breakup of the supercontinent Rodinia in the same way, really, that the York Haven diabase and the Rossville dikes that we talked about last episode represent the breakup of Pangaea. These represent the breakup of a supercontinent called Rodinia, which this breakup ended up forming an ocean that was the pre-Atlantic Ocean.
I call it the ancestral Atlantic,
Okay, there we go. The Atlantic before the Atlantic.
That's right. So Jesse, the two main rock types, right, that are involved here. You have the Catoctin Formation, which involves basalts and rhyolites, and we're going to talk about that because I think that's a pretty cool story that we can tease out a little bit. And then you have this kind of sedimentary cover, the Chilhowee, which is slightly younger. After the volcanism, then you kind of had this shallow marine sedimentary rocks deposited on top. So let's talk a little bit about that. The Catoctin Formation, these basalts and rhyolites.
I'm going to skip ahead real quick, Chris, here, because there's most of the highest peaks in this area are underlain by the Chilhowee. How did you pronounce it?
Chilhowee.
I've said it in my head this whole time as Chilhowee, but I don't know how to pronounce it. So we'll probably get corrected by a listener here. We don't know how to pronounce it.
Yeah, that's all right.
Please correct us. Most of the very highest peaks are this really resistant sandstone, polymicted conglomerates. There's shallow marine delta things that you talked about. These are really resistant rocks. They've been metamorphosed. They experienced a mountain building event when Pangaea came together. They experienced a supercontinent formation event. So they've been metamorphosed and they are really resistant. So a lot of the highest ridges are these sandstones from this Chilhowee or Chilhowee group. Now, there are really high mountains as well that are made of the volcanic rocks, but not quite as high, just because the sandstones, really the quartzites, are far more resistant. And this is just a photo of one of those looking at the Blue Ridge, and you can kind of really get this idea of what the landscape looks like from standing on top of these ridges. And there's all these little rock outcroppings where you can, hike up and stand on these overlooks where there's a bunch of this Chilhowee group sandstone that you're standing on top of, or quartzite that you're looking out.
So, Jesse, if you break apart a continent, you're going to get basalt. We've talked about this. We talked about it in our prior episodes. What about the rhyolite? First of all, rhyolite is very different from basalt. It's much more highly evolved. And we saw some phenomenal rhyolite with some really cool structures in it, too. So what are we thinking about?
I'll skip ahead to image number 4 here, Chris. This is an example of what we saw. I mean, did you think this is one of the prettier rhyolites you've seen when we were on our field trip looking at we were at that reservoir and we were looking at this rhyolite?
Yeah, I think so. I think part of what added to it was that it was spectacularly columnar jointed, and I love columnar jointed rocks. Yeah. Anyway.
Yeah.
And so, yeah, it was It was beautiful. Absolutely.
How does it compare to the flavors of rhyolite, you've seen at Yellowstone, for instance, or out in the western United States? Was it dramatically different, or was it kind of what you're expecting?
No, dramatically different because the color is different. This is more of a dark color. It's like kind of got this, what would you say, maybe a purplish gray kind of hue to it with these phenocrysts in it, these large, feldspar crystals in it, but dark color. And the Yellowstone, most of the rock in Yellowstone is actually like your classic light colored rhyolite look.
Okay.
This is not that.
And I think that's probably has a lot to do with this is really old. I mean, rhyolite, and especially when you get obsidian and glass in there, it's not stable for a very long time. And so this devitrification, or breaking down the glass, is a process that's happened. These are 560 roundabout million years old. They're part of a supercontinent breakup. They've experienced, since they've been on the surface, they've experienced a supercontinent collision and another breakup, and then all the weathering. So they're a bit more tortured than the Yellowstone ones, for sure.
Yes.
And
so how do we get the rhyolites then?
Yeah, so the rhyolites, again, it's one of these things that's not incredibly well studied. So there's a few papers kind of talking about this stuff, but basically you get it by fractional crystallization. We've talked about this at the Long Valley caldera, where the primary driver is basalt down at depth, but that basalt, first of all, it fractionates. You crystallize more mafic minerals, these richer in iron and magnesium minerals that drive up the silica content of the rock. Also, that magma provides a heat source for melting the continental crust. So you kind of you do those processes, this differentiation processes that take you from basalt to rhyolite. And South Mountain, Chris, is a huge rhyolite province. Really thick rhyolites. There's 2 provinces in this Blue Ridge area that have rhyolite in them, and one of them is down south and is older. This one in South Mountain is around that 570 million years old. And so it's fractional crystallization. It's all the things we've talked about before, and we can get rhyolite, which erupts very explosively, typically. And so, interestingly, recent mapping proposed that this actually represented a caldera forming event, a huge caldera forming event, where we're getting kilometers of rhyolite and a big collapse feature in there, and different generations of rhyolite and different flows, debris flow rhyolites, extrusive ones, mud flows, ash fall, all these different types of volcanic eruptions all in one spot. Kind of like Long Valley, I think, in a way.
Yeah.
I kind of, that's where my mind went, was Long Valley, thinking about this.
Yeah, I agree, because of the way that the rhyolite evolves from bottom to top is very similar to what you get with Long Valley. And you can kind of see how the eruptions progressed at Long Valley and how the composition chemically changed with Long Valley from bottom up. And they have the same thing. New research is showing this also with the rhyolites that are in South Mountain. So this...
Yeah. And that was particularly true in what's called the Mount Rogers rhyolite province, which is the one down south. And that's an older one, but kind of similar, analogous to the South Mountain batholith, where you think you have this kind of inverted magma chamber view, because you get this compositional layering difference. So I don't know. When we were walking around there, and reading these things up, reading up on these things, I kind of was getting Long Valley caldera vibes, except perhaps even bigger than Long Valley in some ways, like big eruptions, huge
much
outflows.
Harder though. Right, because the Long Valley is 760,000 years old, and this is 560 million years old. This insane. Is much. Yeah. It's so much more difficult because, like you said too, that it's not very stable at the surface, and it's been there for a long time. And so there's been a lot of changes that have taken place with this rock, just simply because of the lack of stability of like obsidian, glassy minerals, and rhyolite as well.
Chris, those columnar joints have to be the oldest ones you've probably seen, right? They certainly are for me. For columnar jointing, 560 million year old columnar jointing. I wonder what the oldest columnar jointed rocks are out there. I don't know that.
So you see them in the Columbia River flood basalts, but those are under 20 million years old.
Have you seen any up in the mid-continent, up in the UP?
No, I've not seen columnar joints up there. There's rhyolite up there. But so anyway,
so that's
Jesse,
a good point. I mean, but it's a good point, Chris, that there's rhyolite up there in the UP as well, because that's a failed rift system. So you do get, even in these basalt-dominated provinces, you do get rhyolites, right? They're not common, but they're not uncommon either. Like, they are around. You should expect to see them just because of the crustal differentiation stuff that's going on.
One thing I do want to talk about real quick is something that you said to me a long time ago, which is at play here. If you pick up this rhyolite, and how would you possibly conclude that, oh, this is a rhyolite? Well, I think you have to start with, this is an igneous rock, right? That's what you do first. It's not a metamorphic rock. It's definitely not a sedimentary rock. And then, all right, so if once I'm at, this is an igneous rock, how do I arrive at obsidian? Well, I think in this case, you can't really do that until you get it back in the lab, right?
Yeah. Yeah. It's a tough one, Chris. I agree completely. You kind of need to see at the really micro scale what's going on and
What's
look
the
at
chemistry?
the chemistry of these things. Mm-hmm. And you bring up obsidian, which is a really good point, because South Mountain was actually a mining site for Native Americans, because there's a lot of obsidian around here, and so it's a cultural heritage site in many ways, because there are obsidians there. There's obsidian flows there that are really good. And the rocks we were picking up, Chris, were not really obsidian, but you can see how they fracture. This image that we have here, image number 4, you can see how it's fracturing and flaking, and it's definitely an igneous rock. You can kind of feel that as you pick it up. But these were used by Native Americans for making weaponry.
The MVP of all rocks is obsidian.
The MVP. So, there we go.
Right. All right, Jesse, let's move into what happened next. So after the rhyolite formed, the Catoctin Formation, then we have sedimentary rocks. The Chilhowee Formation is on top. But this happened in quick succession, geologically anyway. These are younger rocks, but not by much.
We can treat them as the same package, and a lot of the mapping and literature kind of does. You say, okay, you've got Catoctin Formation, basalts, rhyolites, South Mountain, you have a bunch of rhyolites. There's the Chilhowee group on top of that. That's one package. You have extrusive rocks and sediments. Those kind of go together as a package of rocks, and people map them, kind of as such. What happened next is we have to form this anticlinorium. We have to bend this stuff. We have to fold it. We have to fault it. We have to break it. And that's a really complicated process, as we've described, because this represented a continent breaking apart, and then it experienced continent coming back together and forming a supercontinent, and the Allegheny orogeny and all the complexity of the Appalachians. And then it also experienced the rifting event again, and the breakup and the formation of the Atlantic Ocean. So this is where it gets massively confusing for me, trying to keep all the faulting and fault generations and which ones are which and where are they running, and the naming schemes have changed a little bit. It's so complicated. So I think we just need to kind of keep it.
I think so. What's important here? What's the takeaway with this image that you're showing?
Chris is a little cranky about this right now, I think.
I'm not at all. I'm not. But what the takeaway here is that one of the main faults is this Carbaugh Marsh Creek fault, which in the importance of the Civil War formed the Cashtown Gap.
Yes,
right.
That's right.
And that's the main one that you see on this GIF that you made here. That fault that happened, this kind of strike slip fault, created an opportunity for the Confederates to move through South Mountain and do so quite rapidly and unencumbered.
Yeah. And Chris, this is the one that you can see this on the map view. So here I'm just showing a GIF where we've animated the faults, basically, the major faults that are mapped. And this was some recent mapping done by the Pennsylvania Geological Survey that mapped South Mountain and looked at all these fault structures. So we have a bunch of faults. You just imagine, take this topographic map of South Mountain and there's a bunch of faults running through it. Some of them are reverse faults, which are compressional faults, which is rocks sliding up on top of each other. Some of them are normal faults, which are the extension and kind of pulling apart faults. Some of them are strike slips, they're sliding past each other. Some of them are normal faults that have been rotated to look like reverse faults. And so this is just so massively complicated. But the main ones are the Carbaugh Marsh Creek fault, which we've highlighted here, which kind of cuts right across the center of South Mountain. And you can see this offset. What is it? 3 kilometers, I think, of
3
offset?
kilometers. Yeah.
3 kilometers, where the top of South Mountain has shifted to the left, to the west by 3 kilometers. And you can kind of trace that across there. It's a major fault across this. And that fault goes into the Great Valley and wraps down. And then there's another one that actually had some conflict associated with it, was Monterey Pass, Fairfield Gap, as it's known, which is down to the southwest, which follows the Jacks Mountain Fault for a little bit. And that's where the Union chased the Confederates upon the retreat. There's a little bit of conflict there at the at that pass as the Confederates were trying to escape.
The tail end of the Confederates.
Rapidly.
Yes, absolutely. Yep. By the way, Jesse, it's a 3 mile offset in the Cashtown
3 mile
Gap.
offset. Okay.
Yep.
3 mile,
Yep.
not 3 kilometer. Okay.
Yep.
So a big offset. So I think, Chris, like that's probably enough to cover. But one thing that stood out to me in reading some of this stuff was that the Carbaugh Marsh Creek Fault, which forms this Cashtown Gap, that might have been a fault that was active at 3 different times, or even maybe 5 different times in Earth history. So
makes sense.
It makes sense, right? If you have a weak point, you have a break in a rock. We saw these rocks. We stopped there, and they were trashed compared to other rhyolites. Like they were folded, faulted, quartz veins running through them. They were
Pretty
much weaker
up.
than the rhyolites we saw at the next stop, right? I mean, I got that sense. Did you feel that way too?
Absolutely, because we were right in Cashtown Gap on that first stop, and then we went off from the Cashtown Gap, so off from the fault, away from it, into much more robust and tougher rhyolite for sure.
Totally. Because this fault, and it's moved 5 times, maybe up to 5 times. And you can see if there's a weakness in there and you put some stress on it, the crust, it's going to break along that pre-existing weakness already, right? So it's just going to take advantage of that. That leads to the complexity here, is that these faults don't heal very well. And so you can activate them, reactivate them, fold them, reactivate them again. It gets super complicated. So I think the point of this GIF is just to show there's a complicated network of faults that I can't imagine trying to map this thing. This was a monumental task to try and map all the different rhyolites in here. Holy cow. What a tough job.
Exactly. And you know, I think to tie this in again, when the Confederates were leaving, we're talking about a 40-mile long, essentially like a wagon train, artillery and horses and humans, 40 miles long, moving through this. Well, it's a wide gap, but it's not for that many people. It's not.
No.
They had to utilize as many of these gaps as they could, but the Cashtown Gap was the main one to come in and to leave.
You can see how this would become a barrier, and you want to capture the gap and control that gap and control that pass. In part, I think you can kind of see here the Jacks Mountain Fault kind of runs up to the northeast in that Fairfield Gap, and the Monterey Pass runs up to the northeast and kind of points right towards Gettysburg. And the Cashtown Gap kind of runs through and points right towards Gettysburg as well. So the orientation of these faults and these passes kind of led to the way that Gettysburg, why Gettysburg was a major point of...
Why it all came together there.
It all came together
right.
there because these passes are kind of pointing to it, and South Mountain's kind of wrapping around Gettysburg as well. Protecting it in some way, but also making it a flashpoint. So... What would you do? What would you want to do more in South Mountain? If we did another field trip, Chris, what would you want to go see in South Mountain and look at if we had more time? Because we were busting it. We were making time. What do you want to look at?
You're really putting me on the spot here. You know what? I would want to see the obsidian itself. I'd maybe visit these old quarries. Yep.
Oh, that would be
That's what
really
I would
cool.
wanna see.
Yeah. That would be really cool.
Just to see it.
We saw some of the maps that kind of had a few of them located, but we just didn't have time to go. I'd imagine that's pretty hard to do, hunting around trying to find a quarry site. You'd have to dedicate a day to it, probably at least.
Yep, I think so. Yep.
But that would be very cool. Yeah, I wonder how different the obsidian would look from the rocks that the couple samples that we saw, because some of those write-ups on the South Mountain Geology, the rhyolites were. There's 12, 15 different varieties of rhyolite there, and then obsidian. So I wonder. That's a good one. I'm with you. Let's do it. Let's go do it.
Okay, all right. It's on the books. There we go.
It's on the books. Excellent. Hey, that's a wrap on this South Mountain Geology. This is part of our audiobook series that you can find on our CampGeo mobile app, all about the geology of the Battle of Gettysburg. We're continuing these deep dives. We've got one more left. It's live on the app right now if you want early access to it. You can find us on all the social medias at Planet Geocast. Shoot us an email. Our contact us link is on our website, planetgeocast.com. And leave us a comment if you're on YouTube or Spotify.
Cheers.
Peace.